All right, pipelining को समझने के लिए we have to actually uh, study this parallel processing. All right, so let's study parallel processing and pipelining will be covered alongside it. What is parallel processing? Parallel processing is actually when we have multiple processors, okay, and they are actually either dividing the same program parts and processing those parts in parallel, or we have got multiple processors which are solving multiple programs, which are executing multiple programs. The parallel processing means utilization of multiple processors. Mind one thing, other than this topic, every single topic throughout the syllabus is actually considering one processor at a time. Just this topic is considering multiple processors at a time. So there are multiple forms of this parallel processing. First is single instruction, single data. It is called taxonomy. Like someone once had foreseen this going to moon, and after 18 years we actually went to moon. Similarly, back in 640s or 60s, someone actually by the name Flynn, Flynn, had seen it coming that we would have computers which will be performing at gigantic speed. They would have multiple processors, or if not multiple processor, one single processor will be able to execute multiple instructions at a time. Whatever it is multiprocessing idea. It is called Flynn taxonomy. In your syllabus, this does not go by the name Flynn taxonomy. It is simple. It is how many types of parallel processing do we have? Kind of. It is Flynn taxonomy. So if you like to research on it, go to multimedia and type Flynn Flynn taxonomy. So the first one is single instruction, single data. Now you have to remember back that what is the difference between instruction and data. If I call back in AS, I thought that let's say we have got a program Microsoft Word. That Microsoft Word is instruction set. Every program is a collection of instructions, so it is instruction set. Whereas that file that you make in Microsoft Word or number of files that you create are data. So if we are looking at a program in uh, assembly language, you can differentiate easily between those assembly language instructions and their data. You can, right? Data does not have any opcode and operand, it's just data, whereas instruction has got opcode and operand. Is that understood? So when a single instruction is only acting upon one single data by referring it to, data is always held either in registers or accumulator or memory. Whenever we like to refer to that data in front of an opcode, we refer to it as in constant or address. So when one single instruction, as we have done in AS, is referring to one data item or its memory address, it is called single instruction, single data. Example is von Neumann architecture. This is not parallel in nature. It is not parallel at all. It is part of Flynn taxonomy, so it is appearing in parallel processing. Maybe to differentiate to have an idea that what is the difference between parallel processing and this. But this is actually part of it. It is not parallel in processor. Single instruction, single data. Second one is single instruction, multiple data. It has got two ideas in mind. Few programs are very critical for human life. Let's say autopilot. A plane, when it reaches to a particular altitude and pilot feels like that if it is okay to put the plane on software, they call it autopilot pe chala. What if that autopilot at any given time gets hanged, stuck, sensor is not working properly? How would it actually work then? It will stop. So at such situation where it is critical for human life, you do not keep one program, there rather keep several programs. So that has to be taken into consideration. That several programs means multiple instructions and they all are taking data from the same sensor. This is called multiple instruction, single data. And then single instruction, multiple data. One same instruction, it is being provided with different sets of data. How do we actually look into it? Let's see. Single instruction, multiple data means we are talking about multiple ALUs. What is an ALU? ALU, as I said this morning, is actually the hand of microprocessor. So this ordinary computer here in front of me, we know that with every microprocessor there is one ALU. We have been studying it right from the beginning that what is a computer is composed of ALU, CU, and MU, isn't it? So one ALU is one hand of the processor. So let's see few of the tasks in our life, whether we mean it or we don't, we still like to see those tasks being done by the computer with gigantic speed, the fastest speed possible. For example, you are looking at this screen. This computer screen is still to you. It's not still. Technically, it is being repainted again and again and again, as many as 60 times per second. Every single pixel on this screen from left top to bottom right is being repainted so fast that to your lazy human eye, it appears stationary. And think about a game which you are playing. Think about 4K screen, which has maximum possible number of pixels, and then a game which is requiring high density and a big change on a screen every second. And there is just one ALU. It is painting those pixels one by one from left top to bottom right. You would definitely see a lag. You're playing a game which requires you to change a screen as fast as possible, and one single frame of that screen is having millions of pixels. You might have heard of this Apple's Retina display, and you would still have heard of this 4K screen. There is a difference of 3.2 million pixels in it. 4K has 3.2 million pixels more. And every single pixel from AS and from O level, you must be remembering, is stored and repainted on a screen. So with the game, it is impossible to utilize one ALU. No matter how fast it is, it would be incapable of pasting that screen when it is required. So many times you are concentrating on your character in the game, but the whole environment is being changed. You are, although you are not concerned with it until unless you are focusing on it, yet you like your screen to be changed that way, isn't it? Do you remember old games from Sega where the screen in the background is same and only the character you are concentrating is actually moving? It was because of the slowness of the processor. Nowadays, if you play a game, PS4 and Xbox One and all, there's a big difference. So for pasting on screen, you need multiple ALUs, which for every single ALU, it is necessary that for every frame they distribute their task. Let's say if there are 10 million pixels on this screen, when one ALU is pasting it, no matter how fast it is, it would be slower for me because I'm playing a game. Yeah, it might be okay if I'm watching a movie because I cannot see beyond, like, let's say 22 or 23 frames per second. But if it is a game, certainly I need a faster speed. So what happens? The processor that we call gaming card or things like that are having more than one ALU. So what those ALU do? They divide the number of pixels on every frame among them. So what was happening, let's say earlier, is that one ALU is pasting all those pixels on one screen and becoming slow, no matter how efficient it is now being divided. The number of pixels is being divided, let's say, in four quadrants, and every quadrant is being given to one processor. So uh, the processor that was actually painting the whole screen is now just painting one fourth of it. And alongside that one processor, there are other three processors which are painting this their respective quadrant. That screen is now not being painted from left up to bottom right. Rather, the number of pixels which need to be painted are distributed among the number of processor, and they all are doing their own part at the same time. That is parallelism. So there is one instruction, paint, and every single processor has their own set of pixels to paint. So one instruction, multiple data. So higher the number of ALUs, I've heard that these people at G4, they have came up with one processor with 99 or maybe 100 ALUs. They call it cores, by the way. All right. So single instruction, paint the screen. And multiple data means so many pixels and they are equally divided among number of processors and they are being painted together. So this is called single instruction, multiple data. Also called array processor, used in graphics, related applications like gaming. Examples are gaming consoles and graphic cards. ठीक है, अब इसमें कंट्रोल यूनिट है और इस कंट्रोल यूनिट पे बहुत सारे प्रोसेसर्स अटैच्ड हैं. एक कंट्रोल यूनिट है और हम ये प्रोसेसर किसको कह रहे हैं? एएलयूज को. वन एएलयू, सेकंड, थर्ड एंड फोर्थ. And they have their separate memories because they have different data for every core. So in gaming card, the core is number of ALUs. But in i5, i7, it is actually the complete processor. So they have their separate memories. Is that understood? And if these are not one, more than one, here and here and here, it is also possible. how they would have branches, 99 or 100 branches for 100 processor? It is not possible. So what they do, they are going to plant, and they are planting more than one ALU at one branch. Less branches, more processors, and every processor has got their respective memory area, which is filled with their work, which is mainly to paste the screen. And every single processor is pasting their respective area. So the work that was being done in a single unit of time by one processor is now being done by many processors, yet the instruction is same, paint. It paints the whole screen. So single instruction by the control unit, it goes to every processor, whatever the data that they have in their memory is pasted over the screen. Tell me if you get it. Yes. Obviously, memory inside the processor is in the form of registers bit. For each ALU, it is separate. Have you heard of these bridges and all in processors? Sandy bridge and all. These are actually circuitry which are making sure that these memories are shared properly. The circuits which are actually sharing data do not collide and all. So these are bridges actually. Anyways, हम इसमें बहस में क्यों जाएं, हमारा इतना सारा थोड़ी है सिलेबस. आगे चलते हैं. Multiple instructions, single data. Not very common, and it is actually mostly the software phenomenon, just a form to be utilized mostly in software form. But pipelining is an example of it. Pipelining is something which is still being used in these modern processors even. Well, you get the idea. Multiple instructions, single data, like I tried to explain in case of autopilot. When there are separate and different software, the motive is same, and if one falls back, the other one comes forward and takes the place, and yet they are having the same input from the same sensors. Pipelining, let's just finish this topic and then we start discussing pipelining. Multiple instructions, multiple data. This is what our processors nowadays, desktop processor, I'm not talking about gaming processor or the cell phone processors. When I say multiple core, actually I mean multiple processor with their own CU, ALU, and MU. The memory. Okay. The processor that you see nowadays, it's jacket, which is harboring actual processors. If it is i7, 8 cores, means 8 actual processors are inside the jacket, which are sharing the main memory. What is sharing the main memory? Means आप एक RAM लगाते हैं, you just put one RAM, and one RAM is being accessed by all those 8 cores, shared memory. So multiple cores, as in complete processors, not just ALU, working under scheduler. It is having its own control unit. It is scheduler now. We have to study the scheduler. We will study it shortly. So these are, now it is up to the scheduler. Scheduler is being the part of operating system. If it gives the same program to all these microprocessors, or it gives separate programs to these all microprocessors to execute, or it is giving one program to two and another program to two, it's up to the scheduler. Operating system decides for it. For example, if my cell phone has got 8 cores, they're claiming it has got 8 cores, but I am sure that since I have purchased this cell phone, I would not have ever used a single program that will use more than one core. What it is doing, it is running operating system on one core and my programs on another core. So in order to utilize all these cores, you have to have those programs which push the computer to utilize more cores. It's like your brain. If you are a lame couch potato, how much of your brain is being used? It is being rotten. But if you are researching, you have got the same brain. Now you are pushing your brain, it is opening its neurons, and it is now letting you think more and do more. All right, that is what is happening. Even if you are happy that you have a cell phone or computer with so many cores, you have to have such programs to utilize it, otherwise there is no use of it. Go study the manual, it will tell you that at most it will be using 4 cores, and when you play such and such sort of programs like gaming and all, then it opens up other cores. All right, so it is actually dependent over your scheduler, that how it schedules it. All right, so they have shared memory. Now let's see what is parallel processing in actual means. Let's say it is von Neumann architecture, single instruction, single data. Beta, pay attention. We have to add from 1 to 100. Okay? And it is single instruction, single data processor, which is von Neumann. It will add 1 and 2, keep 3. It will load 1 and then add 2, keep 3, and then it adds 3, keep 6, then adds 4, keep 10, then adds 5, keep 15, and go on and on and on. How many cycles it will be requiring? 99 cycles. It is not 100 cycles. Let's say loading. Yes. Okay. 100 cycles. In first cycle it will load 1. In second cycle it add 2, keep it. Then third cycle it adds 3, keep it. And it would go on with every single number. This is one core. How many cycles? 100 cycles with single core. Let's say I have got 4 processors. This is multiple instructions, multiple data. My scheduler will take 1 to 25, give it to one core. 26 to 50 to another core. 51 to 75 to another core. 76 to 100 to another core. Now your work has got reduced by 1/4 automatically because you have got how many cores? 4. But it really does not mean that 100 instructions now will be converted to 25. Now these are 4 instructions, but because they are happening in parallel at the same moment of time, we are considering it as one. So let's say if it was 100 seconds, now it is being done in 25 seconds, but not ideally. How? These 4 they will output their own result. Result 1, result 2, result 3, result 4. These 4 results, half and half, will be taken and given to 2 CPUs now. Their result would come, these are 25 cycles, these are 2 cycles, and then these 2 final outputs will be given to one processor. All right, so how many cycles these are now? 29. Okay, so in von Neumann it is 100 cycle, and if it is 4 core processor, then it is 29 cycles. Now do not think cycle in terms of seconds. Cycles are now in billionth of a second. A giga means a billion cycles per second. If you have a faster processor, a slower processor, yet in human time it is okay with us. Is that clear? So that is how we think of multiple processors, that if the program is written this way, this is another thing. If program is monolithic, it is like a is equal to 5, b is equal to 6, c is equal to a plus b. Until unless you solve a, until unless you solve b, you cannot solve c. So monolithic programs are those programs where every subsequent instruction is basically depending upon the output of previous instructions. If the program is written such way, having 200 cores does not mean anything, because that would not work. beyond one core. In order to do that, you have to write programs which are actually parallel, which can be executed parallel. So that is all different regime. If you want to make a game and you want your game to be executed over multiple cores, you would have to write game in a way that multiple processors can take up with the parts of these games or this program, and they execute their own part. You have to write program in parts then. Is that clear? Not every program, no matter how advanced or older it is, can be executed over multiple cores. You have to write program that way for this purpose. Anyways, let's move on to pipelining. Now, what is pipelining? Pipelining is, we have heard that when Steve Jobs died, there were certain number of products in the pipeline. Means no one would be judging the company for its product for, let's say, up to next 5 years, because Steve Jobs has already planned for the products and they are in the pipeline. What does that mean, pipeline? Pipeline means something which is happening but one after the other. That is pipeline. So in computer, what happens when multiple instructions are being executed, our general wisdom says that one instruction is being fetched and then decoded and then executed. So until one instruction is finally executed, second instruction does not come in. This is what we heard. No? From PC it goes to MAR, MAR points to memory, from memory instruction arrives in MDR, from MDR it goes to CIR, CIR then decodes and executed. Once it is done, then PC sends the address of next instruction. This is, what does it mean? Until one instruction is completed, another instruction will not be started, isn't it? But what if we divide our processor into three parts? The fetch part, the decode part, the execute part. So for the very first time, first instruction will enter fetch part. From that point onward, it goes to decode part. When the first instruction is being decoded, second instruction is being fetched. When the second instruction is being executed in third part, the second instruction that was fetched is being decoded and the third instruction is being fetched. It, at one moment of time, there are three instructions in the pipeline. The oldest one is being executed, the latest one is being fetched, and the one in the middle is being decoded. That is pipeline. As soon as first one is executed, second one will be executed and third one will be executed. When third one will be executed, fifth one being is fetched and the fourth one is being decoded. We have to understand that process. So this is called pipeline. Is it clear? Okay. There we go. This is multiple instructions, single data. Means multiple instructions are in cycle, but the instruction which is executing is only utilizing the data, because other two are either being fetched or decoded. They are not utilizing the data. So the one which is being executed is utilizing the data. So means multiple instruction, single data. MISD. All right. So simple processors complete fetch, decode, execute cycle, complete it once and then take the next instruction. In pipelining, processor is divided into units, which is fetch, decode, and execute. So let's say one program has got 4 instructions. So the first instruction, this is a pipeline. Pipeline is there. Why do we see a chart? Because we are actually noting it down. Pipeline is just that. Instruction executed, other instruction is pushed, then another instruction. This is one single pipeline. Because we are noting it, we write it this way. Otherwise, this one is the pipeline. At this moment, pipeline has got just one instruction, two instruction, but onwards it would have all three instructions in there. Okay, so the new instruction is being fetched, the older one is being decoded, the oldest one is being executed. So these are multiple instruction, and only the instruction which is being executed is utilizing the data. This one line is pipeline, and there is just one pipeline. Some computers have multiple pipelines. Is that understood? Now, pay attention to the fact that we have got one, two, three, four instructions. First instruction is being fetched. The other moment of time it is being decoded. While it is being decoded, third one is being fetched, and then first one is being executed. Second one is all is happening. When the instruction number 4 will be executed, instruction number 4 will be executed, it would have 5 being decoded, 6 being fetched. So although this program has got just 4 instructions, instruction number 5 and 6 is also inside the processor. As soon as instruction 4 is executed, 5 will be executed, 5 will be executed, 6 will be executed. This 5 and 6, these are not part of my program, but these are in subsequent memory addresses, so they are fetched. It is garbage. So let's say I've got 3 instructions. When the third one is being fetched, 4 and 5 are already in the system. These are garbage. What I do, or simply I have got this instruction at number 3 which says jump to 6. It means I don't want to execute 4 and 5. We know what jump instruction is, right? Everyone. So when third is being executed, automatically it would not jump to 6 because the fourth one is in the line. So what happens? There's a term called flush. We flush the whole pipeline. We finish all 3 instructions. And which instruction now enters the pipeline? 6, because that is the next instruction which needs to be executed. Are we good? So why do we flush? To avoid junk being executed. When do we flush? When the program is finished or there's a jump instruction. New program likes to get executed. Flush. Flush means clean the pipeline. There's just one pipeline. Clean it up. Whether it is being executed, whether it is being decoded, clean it up. It's called flush. We know what jump is. Now, your syllabus says that with respect to parallel processing, with respect to RISC, with respect to pipeline, what is an interrupt? So I could find a little about this, little from the Cambridge book, a little from my own knowledge on internet. I am never clear that what they actually mean. I think they mean, this is the best I could understand, that while an instruction is being executed in the pipeline, while the instruction set, a program, is being executed in the pipeline, what would happen if an interrupt occurs? So, acha, and next, this pipeline is with respect to RISC. It is not CISC. It is RISC-minded. It is an old phenomenon. It is with respect to RISC. When interrupt occurs, the instruction that is in execution will be completed, and data along the instruction number from which the cycle will resume is saved in the memory stack, and the pipeline is flushed to cater the program related to the interrupt. This is one general wisdom, knowing what we did earlier, what we learned earlier, and what we have learned just now. There is another pipeline. This is from your book, the CI book. This is another. There is another pipeline that will be used to handle the program related to the interrupt, and the current pipeline is untouched and resume its working once interrupt related pipeline finished working. What does that mean? As soon as there is an interrupt, your pipeline is hanged, frozen, And the pipeline, another pipeline that we have in the system will be tackling with the program related to the interrupt. Once it is completed, this frozen pipeline will be resumed. This is another idea. Otherwise, it is same interrupt that we learned in uh, yes. Now, your book and a past paper question exhibit this pipeline from another point of view. It has got now no three parts, rather five parts. Instruction fetch part, instruction decoded part, memory access part, or operand fetch part. Memory access means, let's say if it is LDD 200, what does that mean? Load directly from address 200. So this is memory fetch part or operand. Memory address is operand. Instruction execute part and write back. Write back means writing back to the screen. We know that our RISC works register to register. So we have to bring the data into the register, we work around it, and we write it back. So it is no more three parts, it is now five parts. So let's say there is an instruction that is LDD 56 and it is loaded at memory address 39. So PC bears what? 39. From PC 39 goes to MAR, PC becomes 40. MAR points to memory location and the instruction arrives in MDR. And from MDR it goes to CIR. This is fetch part. This is what part? Fetch part. CIR then decodes. When it decodes, it finds out that there is an address which is operand. That operand is put back in MAR. This is memory access part. From 56, what arrives in memory? 7. Memory accessed. And then execution of the instruction happens. And then this 7 will be written back to the memory. Now these are 5 parts. Instruction fetched, instruction decoded, memory accessed, instruction executed, and write back. So these are like, let's say, 6 instructions. And we have got a pipeline like this. This is a pipeline, this is pipeline, this is pipeline. Instruction fetched. When this is executed, second is being, sorry, when it is written back, second is being executed. Third one is being accessed. Fourth one is being decoded. Fifth one is being fetched. All right. And these are 6 instructions. When this 6 instruction is being written back, there is a lot of it garbage in the memory. So we still need what? Flush. So this is improper form of showing it. So this is one cycle. All right. Let's see how. This is improper form. This is the proper form. How many cycles does it take to execute a program holding up 6 instructions in the pipeline, which is having 5 parts? How many cycles does it take to execute a program having 6 instructions in a pipeline having 5 parts? It takes 10 instructions. Oh, 10 cycles. So this is one cycle. Cycle is what? Unit of time. Cycle is what? Unit of time. Unit of time. So one instruction, sorry, 6 instructions will take how many cycles? 10. आप देख लें. 1, then it is decoded, then it is fetched, and then 6 instruction will be loaded at 6 cycles and will be executed at 10 cycles. You would have such question. One of the past paper questions asked this. There are 5 instructions. How many cycles will it take? 9. If there are 3 instructions, how many cycles will it take? 7. Because it ends at what? Right back. So let's take a break for half an hour. Let's meet back at 11:45. This is 11:15. So Bandar. 11:15.